let's make sure I'm recording this. Alrighty, guys. So the last thing we had talked about were these basic sine, cosine, tangent inverse functions. We had also looked at just how to use a calculator to evaluate our functions over here. And then we had also talked about how we can use triangles. So I was looking at my notes from last class, and I don't think we made it to try it now, number 3, as far as I could tell. So that's kind of where I want to pick up. Now, we did talk about how we can also use the right triangle trigonometry, basically to help us come up with the value of our angle, because basically that's what the inverse function does, right? It helps us figure out what the value of our angle is going to be. Oops, sorry. So as you can see with this guy, and I'm looking at example 3 over here. With this one, you can see we have the angle theta over here. This would be the adjacent side. This would be the hypotenuse. So of course, using the definition of a cosine function, we know it's going to be the adjacent side over the hypotenuse side. So you get cosine of theta is equal to 9 over 12, right? So then when we can use the inverse function, and again, basically, you are doing a simple algebra over here. So if you have cosine of theta equals 9 over 12, think about it. If we wanted to get theta by itself, we would try to get rid of the cosine value over here. And that's where the idea of the inverse function comes in. So you can say, okay, I'm going to apply the inverse function, which technically is not the same as division, but you're kind of using the idea of, I want to get rid of the cosine function, so I use the cosine inverse, right? So you're using the opposite function. Remember how we talked about subtraction is the opposite of addition, division is the opposite of multiplication. So you're kind of using that same idea here. So since we know cosine and cosine inverse are obviously inverse functions of each other, you use that, you get theta by itself, and you can see that's how we land up with cosine inverse of 9 over 12. And then based on, do they want the answer in radian or degrees, you can basically put that in your calculator, and you can see this gives us a radian value of 0.7227, or you can convert that to degrees at 41.4096 degrees, right? So that's kind of how you can use the right triangle trigonometry also to help you come up with the value of your angles. Alrighty. Let me know if you have any questions on this example here. Okay, now let's see what happens if we try to plug in different trigonometric functions. And we had kind of talked about composition also, where we had talked about, you take the inside function, evaluate that first, and the output from that inner function will of course then evaluate the outer function. So again, just a very quick review over here. You will start by evaluating what is cosine of 13 pi over 6, and then basically, like I said, you can use unit circle, you can use just simple solving of the cosine function at this value, but you will see this guy comes out to be square root of 3 over 2. And again, I do have the unit circle up here, so you can kind of figure out, okay, if I'm talking about square root of 13 pi over 6, well, where is that going to be? And remember, we had talked about, you can use the idea of the coterminal angles. So your 13 pi over 6 actually coincides where pi over 6 is going to be. So you can see that's where we're getting the square root of 3 over 2 value. So once you get that, that answer becomes the input of sine inverse. And then, of course, we figure out, okay, for the sine inverse, what should that angle value come out to be? And again, you can go back to the unit circle and you can see square root of 3 over 2 for the sine function happens at the angle pi over 3. So using this idea, I believe this is where we had stopped. So I'm hoping that we can work on number 3, cosine inverse of sine of negative 11 pi over 4. So take a minute, think about what this guy should come out to be, and like you normally do, share your answers directly with me, not with everyone. So cosine inverse of sine of negative 11 pi over 4. And since you have that negative inside of the sine function, remember you can use the idea of odd and even functions to help you simplify those answers. Does anybody remember if sine is a odd or even function? Well, I hope you do remember since you will be testing on this next week, right? Is sine an odd or even function? Yeah, very nice. Very good. Let's see. I have Mav in there. Very nice. Yes. So the um fact that sine is an odd function, and I've got Mickey in there, Musab, very nice. So yeah, that means you can actually bring that negative sign outside and you can say, okay, let's evaluate sine at pi over 4, right? And then you can get the value that way. And I'm already seeing answers coming through. So Janice, I'm not sure why you're getting, sorry, I missed an 11 in there. That should be 11 pi over 4. Where's my eraser? There we go. So that's negative 11 pi over 4. There we go. So bring the negative outside and you've got 11 pi over 4. Okay, very good. Alrighty, let's see. I've got a couple more answers. So yeah, Mickey, we're not using the calculator in this. We are looking for exact answers, so I do not want decimal answers. So the first question is, where will 11 pi over 4 fall on your unit circle here, guys? Because if you look at, and let me come back here, if you look at the unit circle, you don't have 11 pi over 4 distinguished, right? It's not shown to you. So where would it fall on the unit circle? So remember, since it is given to you as a negative angle, you can think about going in the clockwise direction, or like we said, since this is an odd function, um, yeah, you can think about it as coinciding, bringing that negative out and then saying, okay, which one is it going to coincide with? And actually, it is going to coincide with 3 pi over 4. I know some of you have used 5 pi over 4, but think about this. Let me get my little pointer out here. So you've got 1 pi over 4. Of course, this guy becomes 2 pi over 4, which reduces down to pi halves. 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 9 pi over 4, 10 pi over 4. This guy here technically becomes 11 pi over 4. Um, and then since we're bringing the negative sign outside, as you can see, this will then end up becoming negative square root of 2 over 2. And that's again using that idea of the odd function. So that negative sign will stay and it becomes square root of 2 over 2. Okay, Mickey, I'm glad that helped. And then once you get that answer, then remember that becomes the input for the outside function. So cosine inverse will now have to be evaluated at negative square root of 2 over 2. So cosine inverse, is that an odd or an even function here, guys? What is cosine inverse? And we did talk about this last time in class. So cosine inverse, is that an odd or an even function? Um, Yeah, so that actually makes it, Wyatt, an even function. So remember we had talked about how a cosine inverse function absorbs the negative. So you are going to basically be evaluating cosine inverse at square root of 2 over 2. Yeah, Wyatt, exactly. Cosine is inverse is going to be an even function. So what did you guys get as your final answer? And I think I had some answers at the beginning there. So let's see, I've got Phoenix in there. That looks good. Janice, that looks good. Isaac Buckles, Braden, very nice. Jeff, yeah, very good. And Wyatt. Yeah, very nice, guys. So yeah, now you are figuring out, okay, at which angle is the cosine value basically going to be square root of 2 over 2? And again, if you come back and look at that, it's actually going to be right at 3 pi over 4. But remember this one here, since you're kind of absorbing the negative sign with the cosine inverse, it's actually still going to be at square root of 3 pi over 4, going by this original cosine value over here. So that will end up giving us, where did my pen go? There we go. 3 pi over 4. Alrighty. So that was just using composition of functions. And again, guys, I would recommend that if it's been a while since you have done composition of functions, I would definitely recommend you guys to take a look at a review on composition of functions, okay? Alrighty, let's come back to our next example. And you can see now we are taking the inverse function and we're putting it on the inside. So you've got sine of cosine inverse of 4/5. So again, obviously we are saying, okay, you're finding out the angle where the value of cosine is going to be 4/5. So cosine inverse of 4/5. And as you can see, they're writing it out as cosine theta of 4/5. So the idea is, okay, where do we find the sine function, which will help us solve this one? So we're actually going back to using the Pythagorean identity that we had seen, what was it, section 1.2, or one of those where you're using sine inverse plus cosine inverse is equal to 1. And in this case, you can see since we rewrite that cosine inverse of 4/5 as cosine theta equals 4/5, you can use that to substitute for the cosine function in this identity. So you replace cosine squared with 4/5 squared. Go ahead and simplify that, which will of course come out to be 16/25. You subtract it, move it to the right-hand side, and that's where we're getting 1 minus 16/25 coming from. And then, of course, go ahead, simplify that. Since you have sine squared, we would need to use a square root. And you are getting two separate answers, right? Because a square root gives you two roots, one positive, one negative root. And that's kind of where you then have to decide, okay, which quadrant am I going to be in, and where do I get a positive or a negative cosine? So they are saying, since we know that the cosine inverse is always between the angle 0 and pi, so we know that's quadrant 1 or quadrant 2, right? So the idea is, in both of those quadrants, your sine function is going to be positive, and so that's why you discard the negative root and you only keep the positive answer for your sine function. So sine comes out to be 3/5. So you can see in this case, you have to use a little bit of a different approach when you're solving, when you have that cosine inverse function. Because, if you go to the unit circle and try to find where is your cosine value going to be 4/5, well, you will notice nowhere in the unit circle you are going to have 4/5 as your cosine value. So that's the reason why we cannot, obviously fall back on the unit circle to do this. So that's where we're bringing in this identity of the Pythagorean identity, right, to help us solve this. Alrighty, so let's take a look at, sorry, let me clear this out. So yeah, we do have one more example coming up. So let's take a look at that, and then we'll try try it now. So same thing here, you can see we have sine of tan inverse of 7/4, right? So in this case, we're kind of falling back on the identities to help us out, but we're going to look at this with the right triangle. So again, when you have tangent inverse of 7/4, we know that can be rewritten as tangent theta of 7/4. So again, using the right triangle, you can see that tangent of theta is defined as opposite over adjacent. So if this is your angle theta, well, then your opposite side is going to be 7. Your adjacent side is going to be 4. So that's the opposite. That's the adjacent, right? So go ahead and figure that out. And then using the Pythagorean theorem, we can figure out what the hypotenuse is going to be. So you can see we put that into our little Pythagorean theorem formula, come up with our hypotenuse, and then based on the value of the hypotenuse, we can come up with the sine function. And you will see that's what we do, because sine, trying to keep my triangle here if I can. So remember, sine of theta is defined as opposite over hypotenuse, right? So we know the opposite side is 7, and then the hypotenuse, as we just saw here, comes out to be square root of 65, and that's what you are going to come up with for your sine of theta. So that's 7 over square root of 65 is what our answer will come out to be. So just two different techniques over here. You can see here we ended up using the Pythagorean identity, sine squared plus cosine squared of theta is equal to 1. In the second example, we basically went back to the right triangle trigonometry and used, opposite over adjacent for tangent, opposite over hypotenuse. Of course, if you had a cosine function, you would use adjacent over hypotenuse. So two different techniques to show you how we can do this. So based on that, what do you think we need to do for number 4 over here, where you have cosine of sine inverse of 7/9? So this is between sine and cosine functions. And let me see. So sine inverse is given to us as 7/9. And if we think of that as theta equal to that, you can obviously translate this guy into sine of theta is equal to 7/9. And then how do you use that idea to come up with the cosine function? So take a minute, think about what you need to do to solve this, and then let's see what you come up with. No, Mav, we are looking for exact answers for this also. Mav just asked if we could use decimals as an answer, but no, we're still looking for exact. That's cosine. Of sine inverse of 7/9. Alrighty, so I am seeing answers coming through over here. Let's see, I've got Janice, I've got Wyatt, Andrew, Braden, Lolly. Alrighty, so I would say Phoenix. Okay. Wyatt, Andrew, you guys need to go back and check your answer. Okay, alrighty. So let me go ahead and clear some of this overlap writing. All right, so we have cosine of sine inverse of 7/9. So of course, like I showed you, we can write that sine inverse of 7/9 as sine of theta is equal to 7/9. Now, since we are talking about using the sine function, there you go, Wyatt, very nice. Isaac Buckles, very good. So since again, like I said, we are talking about the relationship between sine and cosine function, you can actually go back and use that Pythagorean identity where cosine squared theta plus sine squared theta is equal to 1. So of course, we're trying to find out what cosine square is going to be. We know sine is 7/9. So kind of like we had seen in that, what was it, example 4, I think. You're using that same idea over here. So we've got 7/9 squared, which of course, when you square those numbers, come out to be, what is it? Lord, my mind just drew a blank. 49/81 is equal to 1. And then subtract that from 1, because we're trying to isolate cosine square over here. So did I run out of space? No, I'm good. Okay. Cosine squared theta, I am subtracting the 49/81. on both sides. Oh, there we go. Create some space there. Okay, so these guys will cancel out, leaving us behind with cosine squared theta is equal to 1 minus 49 over 81. Now, this one here, you can use, Desmos to simplify it. You can do it by hand. So that part of the math you can do as you are comfortable with. Jeff, that looks good. Mav, that looks good. Very nice. Yeah. And that's kind of where the trick comes in, right, Mav? Because we have to figure out which identity is going to work and which ones may not work, right? So, like I said, we do want to keep this as an exact answer. And so you need to make sure you are keeping fractions and not decimals, right? So you can see when we do 1 minus 49 over 81, that's going to give us in the fraction form 32 over 81. So this guy becomes 32 over 81. Now, of course, since the cosine is a squared value, we will need to Phoenix, I will need to look at that calculation because you are falling back on the Pythagorean identity on that, basically, right? And I will need to see how that math comes out. But yes, I would say the trig identity of sine square plus cosine square is definitely a better option because that may not always work in all cases, right? So when you take square root with the square, remember you get one positive, one negative root, and then of course the square root is helping you cancel out the square. So you can see this guy will now become cosine of theta is equal to plus or minus. Now we know square root of 81, of course, will go back to becoming 9, but it's the square root of 32 that we need to simplify. So 32, remember, can be written down as 16 times 2. You can also start with like 4 times 8 and then, break down the 8 again as 4 times 2. But if you can go with the highest possible factoring, then that helps out, right? And in this case, we can see 16 will be the largest number that can be taken out of 32. So there you go. And then you've got plus or minus. Square root of 16 comes outside of 4. The 2 will stay inside the radical. And then you get 9 as your denominator. So I know that most of you gave me a positive answer, but can you tell me how we know this value should be positive and not negative for the square root of, for square root of 2 over 9? Why should it be a positive value and not the negative one? And we kind of talked about that in that previous example we saw, but I want to make sure you guys understand which value to choose for your cosine. Okay, I'm seeing something come through. Okay, so I've got Musab saying because it's cosine function, so it absorbs the negative. So that's when we're simplifying, but that's not the reason why your value should come out to be positive. And then Jeff, you said because sine inverse is the range of negative pi halves to pi. Yeah, very nice, Jeff. Very good. So since we know that the sine inverse function can only go from pi halves to negative pi halves, which remember that's quadrant 1 and 4. So in that case, yeah, there's only two quadrants that this can fall into. And of course, we are going to be in, you can see cosine function is going to be positive depending on whichever quadrant you are in. So it doesn't matter. Either way, your cosine function should be positive, and that's what you're going to end up with here is cosine of theta is going to be a positive answer. So positive 4 square root of 2 over 9. So you're discarding the negative answer. Alrighty, perfect. Very nice, guys. Good job. So that was your number 4. Any questions before we move ahead on that? Okay, so basically, Phoenix, you went with the right triangle function to help you solve that. I see where you're coming up from. Okay, all right, very nice. So yeah, technically then you are using what we had done in this example here, right? In example 6, so that's kind of the technique that you used with this. Alrighty, guys, if you don't have any questions on the try it now number 4, let's go ahead and move on to our next example here. So this one is talking about using algebraic expressions within the composition of functions and using that to break this guy down and evaluating our function expression here. So you can see this guy here, we have cosine of sine inverse of x over 3, and they're telling us the value of x is going to be between negative 3 and positive 3, including the endpoints, right? Because you've got less than and equal to in both of them. So we're basically saying x can be anywhere between negative 3 and positive 3, and that's including the endpoints. All right, so again, we can rewrite that sine inverse of x over 3 as sine of theta equals x over 3. Using that Pythagorean identity, you can see we can replace the sine squared with x over 3 squared plus cosine. Go ahead and solve that like we did in the previous examples, and you can see this ends up giving us an expression which is going to look something like this. So you did basically 1 minus x squared over 9, and you can imagine if you're doing 1 minus a fraction, you find that common denominator, which will end up giving us 9 over 9 minus x squared over 9. So keeping that common denominator, we can say, okay, we have 9 minus x squared. And then, of course, to get cosine by itself, you end up taking that square root. And then just simplify that. You can take square root of 9, which cleans up into a 3. And then you only have the square root left on the numerator, right? So cleaning that up, we're basically now trying to say, okay, if we have kind of come up with a general idea of what the value of cosine should be. Now let's go ahead and break this down. So they are saying, since we know that the inverse sine must give us an angle which will stay between negative pi halves over pi halves, then we can basically say the sine function again is going to be positive, which is the logic we used in our try it now example just now. So in this case, we are saying that you are basically going to go with a positive root over here. And then you can see basically, again, you're discarding the negative sign and you're coming up with a positive sign. So the difference in this example is you're not given the exact value. We're saying if your sine inverse is x over 3, and 3 can be a number between, x can be a number between negative 3 and positive 3. Just based on that general algebraic expression, can we come up with a value for cosine? And then you can see we ended up with square root of 9 minus x squared divided by 3. And then we decided based on the value of the sine inverse, your cosine should be positive, and we came up with that. So now you can plug in the values of 3, and then you can see what this function definition is going to come out to be. So it doesn't have to be like at an exact value of an angle or at an exact value of the sine function or cosine function. You can also do it in generic algebraic expressions and still come up with an answer like we saw in that example. So let's try and break this down for number 5. So same thing's happening here. You have sine of tangent inverse of 4x, and they're telling us x value is going to be between negative 1/4 and positive 1/4, including the endpoints. So again, take a minute, think about how you are going to simplify this, and then let's see what you come up with. So this guy is sine of tangent inverse of 4x, where your x is between negative 1/4 and positive 1/4, including the endpoints. So what would be the relationship between the sine and the tangent function? And like you did before, we can rewrite that tangent as tangent of theta is equal to 4x. This would be similar to example 6, right? Where you had the relationship between tangent and sine functions that we saw, Phoenix. That looks good, very nice. So between tangent and sine functions, tangent and cosine functions, this is definitely where you want to kind of fall back on that right triangle trigonometry and use that. So I'll give you guys a minute or two and let me see if you can break this down. So what do we think our breakdown should look like? Now, it doesn't matter where you place your angle theta. Mostly we're used to putting it kind of at the bottom end, but if you put it at the other angle also, the math is not going to change. So honestly, it doesn't matter. So based on that angle theta, this guy becomes the opposite side. This is the adjacent side. This is the hypotenuse. So how can we rewrite that tangent of theta equals 4x based on our little right triangle here? Because remember, tangent is defined as opposite over adjacent. So how can we rewrite that guy? If you only have tangent of theta equals 4x. Thank you for letting me know, Musab. I do appreciate that. Thank you. Yeah, very nice, Phoenix. That's exactly what it's going to be. So since we need it to be a fraction, you can actually rewrite this as 4x over 1. And so the 4x becomes the opposite side. And then, of course, the 1 will become the adjacent side. So yeah, we can use that to kind of break this down. And so that means you would be going back to the Pythagorean theorem. That should be an O in there, guys. So Pythagorean theorem, which in this case would translate as the opposite side squared plus the adjacent side squared equals the hypotenuse squared. Or remember, it's a squared plus b squared plus c squared. So our opposite side is 4x. We're going to square that. The adjacent side is 1. Square that. And then based on that, we need to find our hypotenuse. And I'm just going to call it h for now. So we know that we're trying to find the hypotenuse. So obviously, as you can see, this guy will end up becoming 16x squared. The 1, of course, is just going to be 1 squared, and then this is our hypotenuse over here. So then you end up taking a square root, right, to get the hypotenuse as a single measurement. And you can see this is where this guy is going to break down into a positive or a negative. So what are you going to use, positive or negative for the hypotenuse? What do we think here, guys? When you take the square root, should you get a positive or a negative answer? Yeah, because this is the side of a triangle, right? We're talking about a length of the side of a triangle. So yeah, Braden, Mickey, very nice. It is going to be a positive value over here. So yeah, very good. Alrighty, so now that we have our well, hypotenuse calculated, we can now go back to our sine function. So of course we define sine, and I'm just going to do that on the side here. So sine of tangent inverse of, what did we have? 4x originally will come out to be sine of, trying to see how do I want to write this, sine of theta, which would be basically opposite over hypotenuse. So that, of course, as you can see, will come out to be the opposite side was 4x, and then the hypotenuse is this square root that we just came up with, so 16x squared plus 1. So this is what your final function definition is going to come out to be. So this is what we are looking at. Question on this example here, guys? So using either like Pythagorean identity or using the right triangle, you know, kind of depending on which functions you are using and what relationship we can come up with. So no, Andrew, there will be no square root on the top, and I can show you that. Give me a quick second here. If we go back to our triangle here, you will see the opposite side, since that had come from the tangent function, was only 4x. So your opposite side is going to be 4x, and then the hypotenuse that we just calculated was the one that had come out to be the square root of 16x squared plus 1. So your square root is only going to be on the denominator. And then normally we do not leave square roots on the bottom, but of course you can see, since this is in a generic algebraic expression, right? We don't really have a value for x squared. We cannot really rationalize our denominator and simplify this. So for this purpose here, we will leave the radical on the denominator and we're not going to rationalize it. And then remember, our x value is still going to be between negative 1/4 and positive 1/4, because that does not change, right, as we are evaluating this function. So just kind of remember that. All right, very nice. Good question, Andrew. Any other questions on this example here, guys? Alrighty, so that was actually the last part of section 6.3, or as we're calling it, section 2.3. So again, you can see a bunch of examples at the end here, guys, if you wanted to get some more practice. You can see there are some examples here using the cosine and the tangent inverse, or tangent and cosine inverse function. So that might not be something, to try. That might be a good thing to try just so you can get some extra practice. Alrighty, let's move into our next section, and this is where we're getting into trigonometric equations. So let's take a look at this. Okay. Oops, sorry, that's too big. Alrighty, so here we're talking about, again, we had talked about in the first section that London Eye Ferris wheel example, and we had come up with this little equation for it. And remember, this was telling us where the rider would be, at what height, based on how long the revolution had been going for, right? For how long they had sat in the Ferris wheel. So h of t was equal to negative 65 cosine of pi over 15t plus 70. So they're saying if we wanted to know the length of time during which the rider is more than 100 meters, 100 meters above ground, we would need to solve the equation basically using trig functions, right? So in this case, we're basically saying you know the height and you want to figure out what the time is going to be. So let's take a look at some examples over here. They're saying, okay, so using the known values, we can solve this. So we learned that sine and cosine functions are commonly encountered angles. We can use these to solve equations that would be involving sine and cosine functions at, some of the common angles. So let's take a look at this here. So this one is telling us, again, sine of t is equal to 1/2 for all possible values of t. So this one is basically saying, this is asking us to identify all the angles t where you would have the value of sine is equal to 1/2, right? So at which values of t would you basically see 1/2 as your sine function value? So you can basically get one single answer when you're evaluating your equation or your function. But the idea is you have to come up with multiple solutions, because we know how it works on multiples, right? And we've seen this in the unit circle. So the idea here we're basically saying is, if you just think about the unit circle, the two common angles where your sine function is going to be 1/2, you can see right over here, the value of sine is 1/2 at pi over 6, and then you will see again the sine is equal to 1/2 at 5 pi over 6. So those should be the two numbers that jump at us right from the unit circle. But then you can actually also have multiples going forward from there, because we know the period of a sine function is 2 pi, right? So you can see how that ties back into when you're solving equations like these. So again, going back just to the sine graph over here, we're talking about, okay, so the sine value has to be 1/2, which is going to be this point right over here between 0 and 1 on the vertical axis, right? On the y-axis. So everywhere where that curve of the sine function is going to cross that little red dotted line, that is where we know the sine function is going to be equal to 1/2, right? So you can see it's going to be positive values and negative values for that t function. So this is where we bring in this idea of the period of a sine function. We know that's a 2 pi. So with these two angles at t equals pi over 6, plus using that multiplicity of 2 pi times k, right, where k can be any integer, positive or negative value, and then you repeat that same thing with the other angle, 5 pi over 6, with again multiples, and that way you are actually covering the entire domain of the sine function, because that k value, being an integer, is just going to keep taking us to different multiples of 5 pi over 6 and through different multiples of pi over 6. So again, if we come back to our unit circle, basically we're talking about that rotation, right? So if you did pi over 6 and you did one full rotation of a 2 pi, well, that will bring us to 2 pi plus pi over 6, right? If you did another rotation, a second one, well, that would be pi over 6 plus 2 pi plus 2 pi, right? So that's how your multiplicity is working. And that's the same thing we can do with negative 2 pi if you went in the clockwise direction. And the same thing's going to happen with 5 pi over 6. If you completed one full rotation, well, that's 5 pi over 6 plus 2 pi, right? And then if you did another rotation and another rotation, clockwise or counterclockwise, so you're always going to be at the multiples of 5 pi over 6 and pi over 6. So that's one thing we have to keep in mind as you are solving these types of equations, because they're asking us to find all possible values of t. So this is not specific to only for this angle, right? Or only for this value of the angle. This time we're saying wherever sine is going to have the value of 1/2, we want to list all of those angle measurements. So are you kind of seeing the difference between what we did in the last section and what we're doing in this one? And you really just have to look at the wording of the problem. So when they're asking you to find all possible values, that's kind of, we know where we have to bring in the multiplicity. All right, let's look at another example here. This one is saying a circle of radius 5 square root of 2 intersects the line x equals -5, and you can kind of see that illustration at the bottom of that example. So they're asking us to find the angles theta between that interval 0 to 2 pi, where the circle and the line intersect. Now, of course, you can see the circle and the line are intersecting at one point over here and the second point over here. So they're saying the x coordinate of the point on the circle can be found by using this relationship here, right? And we had talked about this again in chapter 1, where we defined x as the radius times the cosine of theta function. So your x coordinate will basically end up becoming, radius we know is 5 square root of 2, so that's r as 5 square root of 2 times cosine of theta. Now, to find where the line x equals -5 intersects the circle, well, that's your x value right there. If x equals -5 in this equation, you replace your x value with -5, and now we can work backwards to figure out what the cosine value will be, and then based on that, what the angle of theta will be. So basically, you have -5 equals square root of 5 over 2. Well, go ahead and divide both sides by 5 square root of 2. So this guy cancels out. You are left with -5 divided by 5 square root of 2. Of course, 5 and 5 cancel each other out. You get 1 left behind on the numerator. So with that negative sign, that ends up becoming -1. You have square root of 2 left on the bottom. Now, this is where you would definitely want to rationalize your denominator. So since you have -1 over square root of 2, rationalize it by multiplying both numerator and denominator by square root of 2, which, as you can see, this will then become negative square root of 2 over 2. Again, now we're saying, where is the cosine function going to have the value of negative square root of 2 over 2? And for this one, you can go back to the unit circle, because this is given to us on the unit circle. So you will see at negative square root of 2 over 2, you've got 3 pi over 4, and then negative square root of 2 over 2, you've got 5 pi over 4, right? So 3 pi over 4 and 5 pi over 4 is where it's going to be. Now, can you tell me why we did not do the period option of adding 2 pi times k with both of these angle measurements? So why do we not have 3 pi over 4 plus 2 pi? Because cosine also has a period of. Why did we not write these out? What's the reason? What was the question prompt that was given to us as we started out this problem? Because right over here, they're telling us your theta needs to stay between 0 and 2 pi, right? Yeah, exactly. You cannot go smaller than zero and you cannot go higher than 2 pi. So that's why they did not ask us for all possible values of theta. They're saying find the angles theta that stay in this interval of 0 to 2 pi, right? And that's the reason why you are not having to do that plus 2 pi k, right? You're just sticking with the two. Because, they're being very specific. It's this circle with this line intersecting it, and you're going to be at these two points over here. All right, so let's try and apply this same idea to our example over here. So you can see, try it now. They're asking us to find tangent of theta is equal to 1 for all possible values of t. So here we're definitely looking at uh, the period and the multiplicity, right? Because it's all possible values of t. So this is tangent of t is equal to 1. So what do you think this guy should come out to be? Okay, I'm seeing some answers coming through. So yeah, remember, Mickey, tangent should be equal to 1, right? And you're trying to find what the angle measurement will be when tangent equals 1. And then Andrew, looks like you've got an answer for me there. Okay, let's take a look. All right, so tangent of t is equal to 1 for all possible values of t. You can go back to unit circle to help you out if you're not sure how to come up with that. Because I guess my one hint to you guys would be to think of the tangent function as the ratio of sine over cosine. And you're not going to have too many options, which will give you tangent of t is equal to 1. Any ideas on what that angle measurement would be? Um, Mickey, very good. Yeah. And then what is the period of a tangent function? So remember, we are basically saying if we're taking the ratio of sine over cosine and simplifying that, that should come out to be positive 1, right? Which means both sine and cosine have to have the same uh, sign, right? They have both got to be positive of their, or they've both got to be negative. And then you also have to think about in terms of the period of the function. So which angle would you use? So if you start out with 0, you will see basically as we are moving up on this unit circle, at pi over 4 is where you can see both my sine and cosine values are the same, and they have the same sign also, right? They're both positive numbers, which means when I take the division of sine divided by cosine, I'm going to get a positive 1 from here. And then as you go down, this guy's not going to work because one of them is positive, the other one's negative. If you go down the circle, You will see at 5 pi over 4, it's negative and negative. So this guys will give us a positive one. And then as you keep going, you will see at 7 pi over 4, one's positive, one's negative. So that's not going to work. So in a unit circle, your possible answers are 5 pi over 4 and pi over 4. But then with that idea of a period, you actually do not need to use both angles. And so that's why I'll ask you again, what is the period of a tangent function? So right now, these are the two values you came up with. And Andrew, that's what you had in your initial answer to me. So that's good. But we do not need both angles. And why is that? What is the period of a tangent function? Yeah, very nice. The period of a tangent function is pi. So when you actually just look at the value of pi over 4 with that period of pi times k, where of course k is an integer, it automatically actually takes care of 5 pi over 4 when we do the multiplicities, right? So you actually don't have to write out 5 pi over 4 separately with pi over k, because it basically is part of this answer over here. So yeah, just one angle. This is just from our unit circle that we had come up with these two. But when you write out your answer, that automatically is taken care of. All right, questions on our little try it now example over here. So again, guys, look for the language in the problem. Are they asking you for all possible values? And that is where we bring in the period. Or in this example where they said your angle is going to be between a certain interval, and then that tells you you do not need to go beyond that interval and find anything outside of it. Okay, let's look at this little application over here. So this is talking about the depth of water at a dock rises and falls with the tide, as we would expect that to be. Not just the period, right? You have to do period times an integer, right, Phoenix? So you will do like pi times k or 2 pi times k to show that as the k value will, increase or decrease, that angle value is going to change. So yeah, you do the angle plus period times k, and k is going to be an integer. Yeah, we just use the letter k. Sometimes you will see textbooks use the letter n to represent an integer, but since your textbook is doing k, we're just sticking with k as the notation for the integer. But yeah, a lot of other textbooks will use the letter n. So, it just depends on the author and what they chose. But yeah, that's kind of the general definition. So Phoenix was asking, like we did, pi over 4 plus pi times k. So he was saying, is that the general notation? And yes, that is. So you have your angle measurement and then your period times the integer. So that's kind of how you would write out when they're asking for all possible values of the angle in the given problem. All right, very nice, very good. Okay, guys, so coming back to this example here. So they're telling us this equation will actually represent that depth that we're talking about as the water level rises and falls with the tide. So you've got f of t is equal to 4 times sine of pi over 12 times t plus 7, and they're telling us t is measured in hours after midnight. So a boat requires a depth of 9 feet to tie up at the dock. So they want to know between what times will we get that depth of 9 feet, so we know it's safe for the boat to come in and dock. So when your depth is 9 feet, that means we're looking at the f of t value being 9. So in this equation, you go ahead and replace the right-hand side or left-hand side, however you're writing it out, with f of t being replaced with 9. And then basically we want to go ahead and simplify this equation. So again, basic algebra, right? You start out by subtracting that 7, and you can see 9 minus 7 gives us 2. So that's where the 2 is coming from. Then we go ahead and divide both sides by 4. So this guy will cancel out. And 2 divided by 4, of course, becomes 1/2. So now we're basically saying, okay, if sine of pi over 12 times t is equal to 1/2, then at what angle does that happen? So again, you know sine of 1/2 happens at these two equals. So we need to try and use that to basically help us simplify this little expression of pi over 12 times t, right? So this is where you will see down here, we're kind of taking, okay, hold on. Let me clear out my writing here. Okay, so we know that the angles, again, pi over 6 and 5 pi over 6 is where your sine value is going to be 1/2. And they're saying because of the horizontal stretch or compression, it becomes a little bit interesting on, how you would proceed because it's not going to be very clear. And we know there's a horizontal compression or stretch happening because of that B factor. Remember how we had talked about A is the amplitude, B is the horizontal stretch and compression. So that's kind of what they're falling back into in terms of that compression. So they're saying because we know there's a compression, it becomes a little bit less clear on how you're going to solve this. So we actually now go into substitution to help us simplify a little bit of this calculation over here. So you're taking the sine of pi over 12t equals 1/2, and you're actually replacing this value inside the parentheses with u. So we're saying let u represent pi over 12t, and so that will give us sine of u is equal 1/2. And we know 1/2 happens at the angle pi over 6 or 5 pi over 6. And you can see using that period of a sine function, 2 pi times k, where k is an integer, we can now actually go ahead and solve this. So in this little equation that we came up over here, replace the u back to that pi over 12t. So you basically now have, instead of u, we put back the original value. So pi over 12t is equal to one angle here and the other angle here. We go ahead and basically clean up. You want to get t by itself, which means you will go ahead and multiply both sides by 12 over pi. Multiply this by 12 over pi. Same thing's going to happen here. And when you clean that up, you can see this guy will come out to be 2 plus 24k. From the other angle, you're going to come out to be 10 plus 24k. So that is actually telling you, and that 24 obviously is going to represent the 24-hour time cycle, right? And remember, T happens after midnight. So we're basically saying anytime between 2 a.m. and 10 a.m., the dock will be at a depth of 9 feet and it will be safe for the boat to come in to the dock. So that's kind of how that translates from um, the depth, and how do you come up with the time when you are going to have that depth of 9 feet. So that's kind of where you can see this is a little bit more of an involved problem because you're having to solve the equation, do a little bit of substitution to try and come up with the final answer. So think about this, look over this for next class, because we're obviously going to pick an example and try to solve this as we move forward. And you can kind of see some of the more descriptions that they're going with, but we'll try and do something similar next time. So, all right, guys, we're in section 2.4. We should be able to finish this and get into section 2.5 next time. So let me know if you have any questions. I'm happy to stay back and answer any questions. And then if not, I will see you on Wednesday. So have a great day, guys. Keep working on that homework and see you on Wednesday morning. Bye, everyone. Be careful. Thank you. Take care. Bye-bye.